Hello everyone, welcome to this today's video. So in this today's video we'll be solving the problem nodes at given distance in a binary tree. So this is the problem of the day for today on Geeks for Geeks, and it's a hard level question, and the companies tags are Flipkart, Acolyte, Amazon, Microsoft, and five other companies. So this is a pretty good question. So it's all about how are we trying to approach this. So that's all the question here. So let us first understand the question. Given a binary tree, a target node in the binary tree and an integer value k, find all the nodes that are at a distance k from the given target node. No parent pointers are available. So what does it mean by that? No parent pointers are available. We'll see that in the later stages. So you have to return the list in sorted order. Okay. And so we'll be taking. I have tested this example in my notepad. So first, the target node is 8. So this is the target node that it has been mentioned, and k equal to 2. What does that mean? So at a distance of 2 units, we need to find all the nodes that are there from the target node. So at a distance of 2 units. So let us iterate and find what are the nodes that are there at a distance of 2 units from 8. So this is the first distance of 1 unit, and this covers the distance of 2 units. So this is one of the node that we can take. Similar is the case from here. If we can go, it covers a distance of 2 units from 8, and here one distance of 1 unit and distance of 2 units. So this is also one of the node that we can consider, and these are the only nodes that are possible and that are at a distance of 2 units from 8. No other node is at a distance of 2 units from 8. So the answer that we need to finally return is 10, 14, 22, because they have mentioned that it is a like we need to return it in a sorted order. So, and also there is another point that has been mentioned. No parent pointers are available. So what does it mean? So 10 and 14 can be accessed, right? 10 and 14 can be found out just by the normal traversal, like applying DFS. So once if I call DFS on the right side of child of 8, so the tree is like this: 8, 12, 10, 14. So once I call the DFS on the right child of the 8, so then it will call to this, and once I call the left child of 12, I'll be getting this, and right child of 12, I'll be getting this, right? So this is right child of 12, this is left child of 12, this is 12 is the right child of 8. So once I call the DFS here, and again DFS here, again DFS here, I'll be able to access the 10, 14 as well as 10 and 14. But what about the other node that has been left, that is 22? 22 is like you need to get an access to the parent of it, right? So it's connected like this: 20 and 22. So to get an access of 22, you need to go to 20 and then you need to go to 22. But for this to happen, you need to have the parent pointer, right? If I don't have the parent pointer or parent address, how can I go from 8 to 20? That's not possible. 8 to 20 is not possible if I don't have a parent pointer, right? So like we need to construct it. We need to use a data structure to store the parents and all. That's what he's actually asking us to do indirectly. But thing is, we do not have the direct access to the parent pointers. So that is the reason we cannot traverse back. All right, we cannot traverse back. That is the reason. So what is an alternative approach for this? Construct a data structure. That's not a correct phrase to use. Use a data structure. Use a data structure to store the parents. Store the parents of each node. All right. So this is the first and foremost task that we need to do, and that is what even they are expecting us to do. All right. So this is the first task. This is the first task. Alright, this is the first task that we need to do. Use a data structure to store the parents of each node. So now there are various data structures. What is the best data structure to use? Undoubtedly, it is a map. Right, undoubtedly it is a map, because you can store a corresponding, like a parent can have multiple children, right? A parent can have multiple children. So let us assume this part 20, it has two children, 8 and 22. So for 8 even I can store 20, for 22 even I can store 20, right? For like if I consider this as a child set and this as the parent set, I can have two child to be pointing to the same parent. So I can do this using a map. a map is the best data structure to do this, and it facilitates it. So that is the reason we'll be using a map. All right, so we'll be using a map to store the parent of each particular node. All right, so let us construct that here itself. So I hope you people understood what are we actually trying to do. So let us first do the map thing for here. We'll construct it first. So I'll erase these things. Okay. So for this example is what we are talking right now. So I'll be constructing a map here. I'll be constructing a map. So for 20, the map, the parent is, so let us assume these are the like children. These are the children, and these are the parents. Okay, these are the parents. So for 20, there is no no parent, right? So we can put it as null. And for 8, the parent is 20. For 22, the parent is 20. For the 4, for node like this 4, the parent is 8. For 12, the parent is 8 again. For 10, the parent is 12. For 14, the parent is 12. That's it. We are done. So we are done. All right. So we have made constructed the required map where we are showing the children and its particular parent. But how do we construct this? We'll see that in the code in the later stages. Right now, we are just understanding the blueprint of our approach. All right, we are just understanding the blueprint of our approach. How are we trying to handle the question? So we have made the parents and children relation. We are done. And now go to the particular node. Okay, now go to that particular node. What are the node they are talking about? 8. Now what is the approach now? Okay, we have constructed the map saying that corresponding children and parent we have stored. It's fine. Now what is the next stage? Like what is the next approach? And that is actually the final approach, right? That that is the final conclusion to our particular approach of finding this nodes at a distance k. So how are we going to do that? So I'll just erase this. So analyze the things properly. So now my target node is 8. Target node is equal to 8. Now what am I trying to find? I am trying to find all the nodes that are at a distance k. Okay, distance k. Here it is 2 units from 8, right? From 8. So I'm trying to find all the nodes that are at a distance k that is equal to 2 units from 8. So how do I do that? I'll do the same thing right now. Just because we did not add the access to the parent pointers, we are not able to go back. Now I have this particular map where I've stored the parent of each and every node. So I can go back. I actually know the parent of 20. I actually know the parent of 8, right? I actually know the parent of 8. So I can go back. I can go front. Basically, I can do this using basic DFS, and I can even go back. I can even go to my parent using this particular map that we have constructed. So we have done that. But what is the logic that we are trying to use is, so 14 is at a distance of 2 units from 8, right? 14 is at a distance of 2 units. But 14 is at a distance of 2 units from 8. All right. But 14 is also at a distance of, it is also at a distance of 1 unit from 12. So what does that mean? But why is it 1 unit just from the 12? Because it's just the other level, it's just in the bottom level of 12. So it's just the child of 12. And what is 12? 12 is at a distance of 1 from 8, right? 12 is at a distance of 1 from 8. So basically, what are we trying to do is, we are trying to find the distance. We are trying to find the distance attested with a particular node. So 8 is at a distance 2. 12 is at a distance 1. 14 is at a distance 0 with the reference of 8. All right, with the reference of like 8, we are trying to find the distances of each and every particular node. So 14, once we come to the 14, 2 goes from 1, when we go to 12, and 1 goes to 0 when we come to the 14. So that means we have got we have covered 2 units from 8. All right, we have covered 2 units from 8. That's it. Same is the case for the 10 as well. So 8 is at particularly, like, we are looking out for two distance of 2 units from 8. Now when we have called for the right child, that is 12, now we are only looking at for the children which are at a distance of 1 unit. And now we do it for the next step, that is 10, we have 0 units. That means we have come to that particular node which is actually covered after covering 2 units of distance. All right, after covering 2 units of distance, we have finally approached 10. So that is what we meant. So that is what we are trying to do. So in this way, we are able to find 14 and 10. What about 20 and 2? We can do the similar thing. We can go to the parent of 8. And so once 8 is at, like, we are when we are at 8, we are looking at a distance of 2 units. When we go to 20, that is parent of 8, so then we are looking only at a distance of 1 unit. And when we are going to the next step, that is 22, we are looking at a distance at 0. Like, now we have covered 2 units already, so there is nothing yet left to be covered. So that's it. So we have got the required target required node that is at a distance of 2 units from 8. That's it. So I hope you people understood what I'm actually trying to convey. So this is how you do it. So map is basically used to traverse to parent. All right, to traverse to parent. And the basic things, other things like 10 and 14 can be easily found out. So how are we trying to do that? Using a BFS. All right, using a BFS. So we are trying to find the children nodes at a distance of 2 units using BFS. And also the same thing applies with this as well. We are even trying to get the parent access even with the BFS. So how are we doing it? We'll see in the code. So first, parent finder of root of null. So this is the function that actually helps us to find the parents of each and every node. So this is the parent finder. So you can see I've passed the root, I've passed the parent. Initially the parent finder will be passing the root and the null. All right, because parent of root is actually parents of root is actually the parent. So initially when we are passing the root, all right, so in this case this is the root. All right, in this case this is the root. So this parent of this 20 is null. All right, so this is what we'll be storing here. Parents of root equal to null, so parent of 20 is actually equal to null. And we'll be constructing this following map itself. We'll be constructing this following map here. So parent, and then we'll be calling to the left, we'll be calling to the left, will be calling to the right. And if we find that a particular root is not valid or it is null, we'll be returning it. That's it. We'll be returning from the function. That's it. So this is how we'll be doing the parent finder stuff. And coming back to the original function, so q pair node star end q. So what is this doing? This is what it's storing a pair of node and the distance associated with it. Okay, the distance associated. So what are we trying to store here? So this is the thing. Initially 8, 2, and then we'll be calling its child. It will be 12, 1, and then its child 14, 0. So 8 is the node and 2 is the distance associated with it. So what do we mean by distance associated with it? So at 8, when are we standing at 8, we are looking at a distance of 2 units. Like, we are trying to find those nodes that are at a distance of 2 units. When we are standing at 12, we are trying to find the distance of nodes that are at 1 unit. And when we are standing at 14, we are trying to find these nodes that are at a distance 0 from 14. And distance 0 in the sense that particular node itself. So we'll be taking that. So, all right. So and also bool status is equal to false and find root. This thing is used to find the target node. All right, because in the question it's just been given in the function, it's just the int target, but we need to find the node that's represented it. So for that reason we are using the particular find function. So if root data is equal to target and status equal to false, that means that's the first time that we are encountering something. So because in the question there's a probability that there are two nodes with same value. All right, so there is a probability of this happening. So that is a reason whatever the first node that we are getting it, like whose data is actually equal to the target, we'll be taking that. So target node would be that, and status would be true, and we'll be returning. So because this is the condition that we are using, and status equal to false tells that it's the first time that we are finding something which is actually equal to the target. We are finding some node whose data is actually equal to the target, and status equal to false tells that it's the first time. All right, and it's basic DFS to find the particular target. So these are the two functions that we are taking the help of, and once we get it, so that we are storing it in the target node. All right, so this is the target node. All right, this is the target node. This is where we'll be storing the node which is actually having its data to be equal to the target. Okay, target node data is actually equal to the target that has been given in the question. All right, so nothing to confuse, it's very basic thing. And now we are doing a basic DFS. So for that DFS, we have pushed the target node and its k, and this map is to store the visited thing. All right, so those things that have, those nodes that have been visited already shouldn't be visited, shouldn't be analyzed once again. So that's very important. Nor will be going in a loop, because if I just go call 20, if I just store 20 from 8, all right, if I just store 20 from after calling 8, and if I again try to store 8 in the queue, then it will be a loop. So I do not want that to happen. So once if I go from 8 to 20, I should go to 22 itself. I shouldn't go back to 8. That's not correct. So that is the reason we'll be maintaining a visited map and vector array, a vector int answer. This is the answer, final answer to return. All right, so initially the target node has been visited, so that has been marked as true. So while q is not empty, int size is equal to q dot size. So what does that mean? So particularly at this node, so let us dry run this example. So 28 22, I'll write this here, 28 22, sorry, 22, that should be 4 12 10 14. All right, and okay, this is 22, this is 4 12 10 14. Okay, this is 12, this is 10, this is 14. All right, so I'll just decrease the thickness of this marker. Fine. So we have mentioned this, we have written the diagram for this. So how are we trying to do? Initially we'll be taking a queue. All right, initially we'll be taking a queue, and so first we have inserted 20 here, right? First we have inserted 20, and the distance associated with it, sorry, we have not inserted 20, we have inserted this target. All right, so and the distance associated with this 2 is actually equal to 2. And now once we are popping it out, once we have got this node 8, we are going to its children. So what are its children? 4. So we'll be pushing 4, and the distance associated with it is, see, if the present of left, like if there's some, like the present is the q dot friend dot first, that is actually equal to 8 now, and position is equal to q dot friend dot second, that is actually equal to 2 units. And if present of left, like if there is a child to the left of 8, yes, there is a child to the left of 8, and position is greater than 0, yes, it's still greater than 0. We are still trying to find an element, a node that is at a distance greater than 0. If it is equal to 0, that means we are on the particular thing that we are interested in, so we'll be pushing it back. If not, that still we are looking for it. And visited is false. All right, so we haven't visited this 4 yet, so we'll be pushing that 4 in the queue, and the distance associated with it is 1. All right, and now once again, so we have pushed this. All right, so we have pushed this, and now again, if present of right, so what is it, right? 12. Yes, we have a right child to 8, so we even need to push it. And also the position is greater than 0. Yes, the position is still 2, the position is 2, right? And which is greater than 0, and visited of present of right is equal to false. Yes, we haven't visited 12 so far, so we'll be pushing it 12, and with the position -1. All right, so the position would be 1. And now going to the parent of 8. All right, if parents of present, so like what is the present? 8. And what's the parent of it? Is it is actually 20. Yes, and position greater than 0. Yes, and visited of parents of present, false. Yes, we haven't visited 20 so far, so we'll also push 20, and the distance associated with it is 1. And now coming to the next thing, now int size equal to q dot size. Now there are 3 elements in the queue. Now taking the first element, that would be the 4, taking the first element now, so that is 4. All right, so and we are again trying to check what is its position, that is 1. So we are trying to find all the nodes that are at a distance of 1 unit from node 4, okay, node of data 4. And now if present of left, are we trying to find the life child of 4, there is nothing, so this is kept. And present of right, there is nothing, kept. And parents are present, yes, we have a parents are present, that is actually 8 now, okay, that is actually 8. So the parent is 8, but the thing is the visited is not false, visited is not false, because we have already visited 8, and that is actually true. This has been visited, has been visited, so we'll not be going into this, so it's just over. And now coming to this particular thing, now coming to 12, all right, and the distance associated with it is 1, all right, distance associated with it is 1. And now we are trying to go for the present of pair left, so we are trying to find the left child. Yes, we have a left and position greater than 0, yes, its position is 1. And visited of parent of left is false, yes, we haven't visited 10 so far, so we'll be pushing it. And we'll also make it as true. So 12 has been like 10 has been updated to true, 10 has been updated to true, and we are actually putting its distance as well. So what its distance now, it is at distance 0. So when we call for 12, we have 10 and 14, and when we are trying to push 10, the distance associated with it is 0, because from 12 we are looking at a distance of 1 unit, and from 10 we do not need to look anything, because the answer would be 0. We have finally got that particular node that we are interested in. So 10 is what we have pushed. And even same is the case, we are pushing the other child, that is 14 as well, all right, 14 as well. And once we in the right we are pushing 14, in the left we are pushing 10. And parents of 10 is 12 is already 8, that has been visited already, so we are not going to get into this. And now the last one, 20, all right, so the last thing that we need to analyze is 20. And again the 20's child, left child is 8, all right, 20's left child is 8. So just remove these things, 20's left child is 8. So this has been already visited, so here it will be like this condition will not be satisfied, so we'll not be getting into this. The right child is 22, right child is 22, and it's not been visited yet, so it will be pushed, and with a distance of 0, all right. So 20, when it's called it at distance 1, it will be calling 22, and its distance would be 0, all right. So right now after processing 20, we'll be having this particular things like 12's left, 10 and 14 and then 22, and these are at a distance 0, all right, these are at a distance 0. So once we have got this, now we are going to go into this particular thing. If position equal to 0, this is position is equal to 0 for all these 3 nodes, so we'll be pushing into the answer. And once it's done, we'll be sorting it and returning the array. So that's how we'll be solving this question. It's a like hard question, but logic is pretty simple. It's how we are trying to traverse the other nodes that are not accessible at the very first instance. We need to construct a map and traverse it accordingly. So just the basic thing, just try to dry run with several examples. I hope it will give you an extra clarity, and it's all about making the required functions and following the trace, following the path that you have actually constructed. So that's it for today, and if there are any doubts, please feel free to comment in the comment section. And also the codes in all the 3 languages have been uploaded in the GitHub repo, and the GitHub repo is linked to the GitHub repo is given in the description below. You can just find it out. Thank you for watching. Stay tuned.